Hi, I'd like to get into some more of the single replacement and double replacement reactions here, and I want to show you how you can predict whether a single or double replacement reaction will happen or not. To do that, I'm using this document that I put in the week 8 of the Canvas, and it is called Solubility Rules. I think I showed this to you in the previous video, but now I'm going to show you how to use this. First, let me give you a sample double replacement reaction or double displacement reaction. I'm going to put some lead nitrate, some lead 2 nitrate. This is dissolved in water, a clear and colorless solution, and I'm going to mix that with some potassium chloride, dissolved in water, a clear and colorless solution. And then I'm just going to leave that there, not write the products, because I don't know if when you mix these two solutions together, you get a chemical reaction or not. Maybe they don't do anything. Maybe it's like mixing salt with sugar, like salt water and sugar water. If you mix those, what happens? You just get salty sugar water and nothing happens. So how do you know if something's going to happen in any given double displacement reaction? Well, this is how you know. If the double displacement reaction produces gas, liquid, or solid, then it will happen, okay? There's nothing to see about that. You just have to hear that. If the double displacement reaction produces a gas, liquid, or solid, then it will go. The reaction will go all by itself. And here's what I mean by that. You could see here, these are some rules of solubility. So if you produce some ionic compound in a double displacement reaction, which, according to these rules, does not dissolve in water, that means you produced a solid. And that means the double displacement reaction will happen. You will notice a change. So these are the rules that we use. Let me form the double displacement, the double displacement products for you here. So this is double displacement, just like in the previous video or in the Melissa Maribel video, if you watched that one. We switch partners here, so the PB now takes the Cl, so this is PbCl, but this was Pb2+, and you know that because this is nitrate. Nitrate is 1-, there are 2 of them, so this whole thing, this negative side is 2-, that means this must be 2+. So that, but chloride is 1-, so we must need 2 of these because Pb is 2+. And the other product is potassium nitrate. Right. So these are the products, but is this going to happen? Do these products form? You go back to the solubility rules and you look for your product. So this was lead 2 chloride. So the first rule says compounds containing group 1A metals. Is that lead? Is lead a group 1A metal? Well, let's see. Here's lead down here. That is definitely not group 1A. OMG. So group 1A metals, ammonium, acetates, nitrates, and perchlorates are all soluble. Well, lead 2 chloride does not fall into any of those categories. So I go to the next rule. Most halides. Now halides are group 7A. These are called halides because these are halogens, except for H. These are halogens. When they become negative ions, they are called halides. Like fluoride, chloride, bromide, iodide, these are all halides. So most halides are soluble. Well, lead 2 chloride is a halide, so it must be soluble. Exceptions include silver, lead, and mercury 1 halides. Oh, well, that changes things. Lead 2+ is an exception. So that means lead 2+, if it's mixed with a chloride, lead 2 chloride, that is not soluble. Oh, wow. Okay, so if that's not soluble, that means that this is solid. Once you form a solid in the products, you can be sure that mixing these two chemicals will result in this chemical reaction. What about this guy? Usually, if you formed a solid, liquid, or gas, the other thing is just aqueous. And let's just verify that. I got potassium nitrate here. So I go to the solubility rules, look for potassium nitrate. Oh, look, it says nitrates. Compounds containing group 1A metals, well, potassium is a group 1A metal, there it is, group 1A, are soluble. And also, it's things that contain nitrate are also soluble, so potassium nitrate is just soluble either way. Soluble because of the positive ion, soluble because of the negative ion. So that's potassium nitrate. That's aqueous. Aqueous means dissolved in water. So this actual chemical reaction is pretty cool because if you look up a picture of this, lead, nitrate, and potassium iodide, if you look up a picture of this, you could see the really weird. So yeah, this is a good picture. So you have a clear and colorless solution, which is lead nitrate or potassium iodide, coming into a clear and colorless solution, which was lead to nitrate or potassium iodide. But on contact, they formed this bright yellow solid stuff. You could tell it's solid because you cannot see through it. You're going to do a lab like this next week with Dr. Valdez. Anytime you form a product that you cannot see through, that's a solid. It doesn't matter if it looks cloudy or it looks milky or it looks jelly-like. If you cannot see through it, you just formed a solid. The cloudy appearance or the jelly-like appearance comes from the fact that your solid is made of very tiny particles. And so it doesn't appear like a solid in the normal sense, like a piece of ice or a piece of wood. You know, but it's still a solid. Very tiny particles of solid. So let me give you an example of a double displacement reaction that does not go. I mean, nothing happens. So KNO3, you have let's say you have a solution of KNO3, and you mix that with a solution of sodium chloride. Let's do the double displacement here. The K goes with the Cl, and the Na goes with the NO3. All right. Now, when you mix KNO3 and NaCl, does anything happen? Do you form these products? Well, let's see. Whoops. See, one of the products was KCl. Let's see. Compounds containing group 1A metals are all soluble. Oh, well, K is a group 1A metal, so that's soluble. That means this is AQ. That's dissolved in water. This is another group 1A metal, sodium. There it is, group 1A. So that one is also soluble, AQ. All I needed was rule number 1. How about that? So you see, I started with 2 aqueous things. I ended with 2 aqueous things. I have not formed a solid. I have not formed a liquid. I have not formed a gas. That means this reaction does not go. You do not even have to do this. Actually, you don't. You do need to do this in order to figure out if the products are solid, liquid, or gas or not. But you don't even have to balance this. I mean, your work is done. Once you know that these are aqueous, this is no reaction. If you were to do this in the lab, you might feel the test tube turning cold. So suppose you add this, a solution of this, to a solution of this. The test tube might get a little colder, but that's just because this stuff happens to have that property when it mixes with more water. Now, if you mix it with salt water, this stuff turns cold, not because of the salt, but because of the water. And that is not a chemical change. When you dissolve something in water, that is not a chemical change. It's still potassium nitrate. So that's no reaction, folks. Let me give you an example of something that forms a gas. Suppose I have some sodium sulfite. Sodium sulfite. That's an aqueous solution. And suppose I mix that with some hydrochloric acid. Yeah, aqueous. Oh, by the way, I'm not balancing these. I should balance them, though, because you are civilized students. And civilized students balance their chemical equations. Okay, it's balanced. Now this one. What does this form? Well, this is a double displacement reaction again. This happens to be a special case of the double displacement reaction, but you'll see in a moment here. So this Na goes with this Cl. I already know that NaCl is soluble in water, so I put Aq there. Just NaCl, it is soluble in water because it has Na. Na is a group 1A metal. The other thing is HSO3. Now H is a 1 plus. SO3 is sulfite. It is 2 minus. That means we need 2 H's to make this a neutral compound. Okay, so this is it. They are both AQ, but this reaction does happen. And the reason why this reaction happens is because of this. This forms a gas. There are 3 compounds like this that will form a gas, and you must memorize all 3 of them. Anytime you have H2SO3 AQ as your product, H2SO3 AQ immediately forms water, and there's a water, which is a liquid, and sulfur dioxide, which is a gas. Anytime this appears in the products, that doesn't exist for even a second. It immediately turns into water and sulfur dioxide gas. So because this double displacement reaction forms water, and it forms a liquid, and it forms a gas, because it forms a liquid and it forms a gas, this double displacement reaction goes. You just mix this, and all by itself, it will just start forming water and start bubbling out this sulfur dioxide gas. Let me draw for you the corrected chemical equation, including the knowledge that this produces water and sulfur dioxide gas. It goes like this: sodium sulfite plus hydrochloric acid produces sodium chloride, and not a sulfurous acid, produces water and sulfur dioxide gas, right? So this is something that you need to memorize. Sulfurous acid, AQ, when it is formed as a product of a chemical reaction, it will immediately decompose to water and sulfur dioxide gas, right? So this is the correct chemical equation. Let me balance it for you because you are civilized, so I should be civilized too. I think that's balanced. That's civilized enough for you? Okay, good. Now let me show you the other 2 which you must memorize. So that's one of them down there. That's the sulfurous acid. If you form sulfurous acid as a product, you must immediately decompose that to water and sulfur dioxide gas. Also, if you ever form this as a product, ammonium hydroxide, if you ever make that as a product, as an aqueous product, you will have to erase that immediately, and in its place write ammonia gas and water. Right? If you were to ever make carbonic acid as an aqueous product, not as a reactant, but as a product. If you were to ever make this as a product in a chemical equation, you need to erase that and in its place write water and carbon dioxide gas. Right? You need to memorize these 3 things. Anytime you find this as a product, this as a product, or this as a product, you need to erase that and replace it with these guys. These guys are the products, not these guys. Okay? Just as I did a moment ago. Let me help you to understand why this happens. If you look at this formula, NH4OH here, what happens if you take away H2O? If you take 2 H's out of here, so you take 2 H's out, and then you take an O out, then you end up with NH3. NH3 happens to be a gas. Okay, now, why would you take out H2O from here? It's because anytime nature can do a chemical reaction that forms water, Nature does do a chemical reaction that forms water. Why? Because water is at the bottom of the potential energy hill. So here's what I mean. Chemicals are just like objects in your life. Like objects in your life, like if you put an object on a table, that's a table, and if you put an object such as a cup on a table, this object now has high gravitational potential energy, meaning this object is going to end up down here. At some point in the life of the planet, this cup is going to end up down here, because being up here gives it the potential to be down here. When it comes down here, the potential is lost. There is no more gravitational potential energy. This thing, it has nowhere else that it could go all by itself, so it won't go anywhere unless you move it. So, of course, in order for this to get down here, you have to move it off the table. You're thinking that, aren't you? But see, that's not true at all. You don't have to move this off the table. Eventually, this is going to fall off the table without you doing anything. Why? Because eventually, this table is going to rot, or it's going to rust, it's going to crumble, or eventually there will be an earthquake, or eventually some other disturbance will occur, and this thing is going to fall. It's 100% certainty. In the life of this planet, this thing will fall. So in a similar way, chemicals are like that too. So there are chemicals that have a high chemical potential energy, such as things that are reactive, like bleach or dynamite, or the little capsule of chemicals that causes the explosion that inflates your car airbag when you have an accident. All those chemicals I'm drawing as circles, and they're on top of the imaginary hill of chemical potential energy. Here, let me write chemical potential energy. At the bottom of the hill are the common chemicals, chemicals that we see every day because the earth is covered with them, such as water, or carbon dioxide, or maybe like rust, you know. So things that just form by themselves, you don't have to do anything. You just walk around and you see these things just on the ground or in the air. You notice them somehow. You know, these things are the products of chemical reactions from higher chemical potential energy things. Why is the world covered with water? The world is covered with water because, so there are many different reasons why the world is covered with water. But why does the water stay there? Why doesn't that water react and form something else? Like, if you have pure iron, you're never going to have pure iron for a long period of time. If you have a handful of pure iron powder, just in a couple of days, it's going to turn to rust. But why doesn't that happen to water? If you have a handful of pure water, it may evaporate, but it's still H2O, it's still water. And that water is just going to stay water for a very long time, right? Now, why is that? It's because water is a very low chemical potential energy substance. So at the bottom of the chemical potential energy hill, this imaginary hill here, you have things that have fallen down the hill. So what this means is, anytime nature can make water, that's going to mean that nature can cause some other chemical to fall down the hill to turn it into water and something else. Falling down this hill is a great thing for nature. It happens all the time. You don't even have to do anything. The sun gives enough energy for this to happen. Just the thermal energy in a room gives enough energy for this to happen. So what I'm trying to say is, these chemicals are not particularly unstable. That's not why they decompose so rapidly. It's because this guy is so stable. The water is so low in chemical potential energy, just the slightest nudge, the thermal energy in the room is enough to turn this guy into this guy very fast. And then the other thing is these gases. Nature loves to make gases, and you will learn why in your next chemistry course, Chem 101 or perhaps 102. It has to do with form of energy accounting called entropy. But enough of that. Please memorize that these three chemical equations. Please memorize that anytime you make this as a product, you will form these products instead. Anytime you make this as a product, you'll form these products instead. Anytime you form this as a product, you'll form these products instead. And that is how you predict what is going to happen in a double displacement reaction. I mean, that is how you predict if a double displacement reaction is going to occur. If it forms liquid, gas, or solid, it will occur. If it does not form liquid, gas, or solid, it will not occur. Nothing will happen. Okay? I'm going to do the single displacement reaction predictions in the next video. Thank you.